my name's Juliet Tang, and during this presentation, I'll be guiding you through some of the procedures we've developed for rearing the diamondback moth. Before I start, however, I'd like to outline some key points that would be important for any insect rearing program. The first is hygiene. Working areas, rearing cages, rearing rooms, etc. should all be kept clean and regularly sterilized with 0.5% sodium hypochlorite. That's the same thing as 10% Clorox. The second point is initial gene pool size and genetic mixing. Always start colonies with as many insects as possible and make sure to mix the gene pool each generation. The third point is keep good records. Early signs of unhealthy larvae are lengthening development times, or if it gets worse, an increasing number of larvae dying from disease. And fourth point, stick to established schedules and procedures. Changes which to you may seem insignificant can sometimes have drastic effects on the health of the insects. Diamondback moth larvae in particular are very sensitive to stress. If you follow our instructions, we guarantee that you'll be able to produce thousands of adults which from all outwardly appearances are disease-free. For us, every Friday is our diet day, so our first job is to get the eggs from the diet-reared colony. In this chamber, we maintain 27 degrees Celsius temperature, 16 hours of light, 8 hours of dark, and 50% relative humidity. Inside the chamber, we have 2 oviposition cages that we set up every week. Adults are closed from pupae, mate, and lay eggs on the aluminum foil sheets you see hanging from the cage. Cages are labeled with the date they're set up, the colony name, and the generation of the eggs laid. We also label the cages A or B so that we know which eggs came from which cage. Now let me introduce you to Jenny Holly, our super lab technician who will be helping us out today. She's just finished wiping the bench down with 10% Clorox, and she's going to get ready to change the egg sheets. She labels each egg sheet with the date, the colony name, the generation of the eggs laid, and the cage letter. After labeling, Jenny inserts the new egg sheets into the cages and takes the old egg sheets out. When adult females are laying eggs, we change the egg sheets every 24 hours. Eggs that we don't use right away can be stored at 6 degrees Celsius up to 2 weeks with little mortality. For the diet, though, we always try to use freshly laid eggs. For the amount of diet that we'll prepare today, we only need half an egg sheet from the A cage and half an egg sheet from the B cage. Jenny will sterilize the eggs in formaldehyde. Because formaldehyde is a known carcinogen, she wears gloves, goggles, and works in the fume hood. We use a 3.8% formaldehyde solution. Each beaker is filled with the solution, and we leave the eggs submersed for 30 minutes. After 30 minutes, the formaldehyde is poured back into its container. We reuse the formaldehyde several times, about a month, before we dispose of it properly as a waste chemical. Distilled water is used to rinse off the excess formaldehyde. Jenny will rinse the eggs 3 times. Then she'll soak the eggs for 15 minutes in distilled water. This rinse-soak process is repeated 2 more times for a total soak time of 45 minutes. After the last soak, the egg sheets are unfolded and allowed to air dry in a clean environment. During this whole process, Jenny still knows which is the A egg sheet and which is the B egg sheet. It will take about 2 hours for our eggs to dry, so let's go make diet. We're just outside our media preparation room, and as you can see, we always keep the doors closed, and if workers have been out in the field, they're not allowed back into the media room in the same day. Ideally, your media preparation room will be like ours. It's completely isolated from the insect rearing rooms, and it's dedicated solely to media preparation. This way, you'll reduce the risk of introducing pathogens into your diet. Behind our media preparation room, we have a smaller room where we store our cups and lids and our non-perishable diet ingredients, which Jenny has started to weigh out. I'll let her explain what she's doing.
I've started weighing out enough dry ingredients for 1 gallon of diet. I will continue until I have in 1 bag raw wheat germ, casein, sucrose, vitamin mix, areomycin, ascorbic acid, propylgalate, Wesson salt, potassium sorbate, cellulose, and methylparaben. And in another bag, you'll have the agar. And now we're ready to assemble the diet.
The first step is to melt the agar. Over here, we have a steam-jacketed stainless steel kettle. When the steam is turned on, it travels between the walls of the kettle, which creates a very hot zone within the bowl. If you don't have a steam kettle, you can use the stove or the microwave. It just means it'll take longer to melt the agar. Jenny will now help us prepare the agar solution. First, she adds 3,000 ml of distilled water to the steam kettle. Next, she's ready to add the 96 grams of pre-weighed agar powder. She needs to mix the agar into this water to dissolve all the lumps. Once all the lumps are dissolved, she's ready to turn the steam on low. As the agar begins to heat, she uses a thermometer to monitor the temperature and continues to stir. As the agar heats, it will begin to thicken. The agar will start to boil at its edges, with some signs of boiling at the center. When the temperature reaches 87 to 90 degrees Celsius, the steam should be turned off. Keep stirring, though, until all the boiling has stopped. It's important not to overcook or undercook the agar. The cooked agar should now cool for about 10 minutes. When the agar has cooled to 80 to 85 degrees Celsius, it's ready to be poured into the blender. At the blender, we're ready to add the liquid ingredients. Jenny has pre-measured out 26 mils of linseed oil, 9 mils of 43.6% potassium hydroxide, and 3 mils of 38% formalin. She adds each liquid ingredient to the agar in the blender. Next, she's ready to add the pre-weighed out dry ingredients. Using a wooden spoon, she mixes everything in well by hand. She scrapes down any dry ingredients on the sides of the blender. When everything is well mixed by hand, she puts the lid on the blender and then blends on low for 1 minute. After blending, the diet temperature should be about 75 degrees Celsius and should still pour easily. Jenny is pouring diet into each cup and filling to about 2 centimeters, which means 80 to 100 mils per cup. You should have enough diet to fill 50 pint styrofoam cups. When all the cups are filled, we let the diet cool and dry uncovered for 2 hours. We've now waited 2 hours and the diet is ready to be infested. Diamondback moth is sensitive to overcrowding, so for 80 to 100 mils of diet, we only infest about 300 eggs per cup. Jenny has cut several examples of what she estimates to be 300 eggs, depending upon the egg density. Jenny is now getting ready to infest the eggs. She has one pile of A eggs already cut into groups of 300, and another pile of B eggs also cut into groups of 300. To maintain the gene pool, Jenny will infest 25 of the cups with the A eggs, which are color-coded red, and 25 cups with the B eggs, which are color-coded black. She'll put one A sheet into each of the A cups and one B sheet into each of the B cups. She's also labeled the lids with the date and the egg generation number, and if your lids have holes in the center like ours do, we tape the holes shut to keep the diet clean. We're back in the rearing room where Jenny is putting the infested cups of diet on their side so that frass doesn't accumulate on the diet. At our rearing conditions, which are 27 degrees Celsius, 50% relative humidity, and 16:8 light-dark photoperiod, it will take 10 days for all larvae to pupate. It's been 10 days since we infested the diet with the eggs. We're now ready to set up 2 oviposition cages. As you can see, the cups marked in red originally came from the A oviposition cage, and the cups marked in black originally came from the B oviposition cage. The pupae are freed from the diet by cutting the lid off the cup about 2 centimeters below the top of the cup. Under the lid, we find that the majority of larvae have pupated with about 150 pupae per lid. At this point, if your rearing operation is going well, you should see no disease, no cannibalism, and all pupae should have developed on schedule. Our oviposition cages measure 39 centimeters on all sides. For this size cage, we add 12 to 14 lids, or about 1,500 adults. To make sure that the gene pool is mixed, Jenny will put 6 of the red lids with 6 of the black lids. Adults are fed 10% sugar water that has a little bit of yellow food coloring added. For each cage, we fill 2 50 ml flasks with the sugar water and add a dental wick so that the adults can gain access to the sugar water without drowning. The sugar water is then added to the cage and the sleeves are tied shut. The cages are then returned to the rearing chamber. In 2 days, most of the adults should have closed. Egg sheets are then put into the cages and changed daily. The egg laying period lasts about 4 to 7 days, during which you should be able to collect thousands of eggs. One procedure we haven't gone over yet is how we make our egg sheets. Different labs use different methods, but I'll show you how we do it in our lab. Our oviposition substrate is aluminum foil. The foil is cut into 11.5 centimeter wide by 30 centimeter long pieces. It's folded in half so that there's about a 1 centimeter overhang. This tab is then folded over again. A hair pick or several probes taped together is used to make parallel grooves along the length of the egg sheet. Once we have about 100 of these egg sheets, Jenny's ready to make the cabbage juice.
So for the cabbage juice, I've weighed out 65 grams of cabbage and measured out 500 ml of distilled water. I will now stick them all in the blender. I'm going to blend on high until the leaves are well chopped. When the blending's done, we'll pour it into a flask for it to be autoclaved for 20 minutes. So make sure you put the aluminum foil loosely on the top before you stick it in the autoclave. Now it's ready to be autoclaved.
Here comes Jenny with the cabbage juice. It's already been autoclaved and brought to room temperature. She strains the juice into a rectangular pan to remove the leaf pulp. The cabbage juice is necessary because it helps stimulate oviposition. Once she's finished straining out the leafy material, she dips each sheet individually and sets it on its side to drain. She keeps repeating the process until she has no more juice left. Once all the sheets are dry, which takes about 30 hours, she'll collect all the sheets, put them into a covered box, and keeps them stored in the freezer until she's ready to use them. We have found that unlike our laboratory rear colony, which has been selected to feed on artificial diet, field-collected larvae do not survive well on diet. Therefore, when we collect larvae from the field, we bring them back to the lab and rear them on foliage. We'll start by showing you how we set up our oviposition cages. When larvae have pupated, they're brought up from the greenhouse, and Brenna Mitchell, another one of our super lab technicians, will demonstrate as I narrate. The cages are then put into an environmental chamber which is set at 27 degrees Celsius, 16:8 light-dark photoperiod, and 35% relative humidity. Once adults start to eclose, Brenna will collect from the cages daily. She assembles the collection tube, which has small glass tubing in a rubber stopper at one end, and a small piece of cloth held in place by a plastic cap that has a hole in the middle of the cap. The collection tube is attached to a long hose, which is in turn connected to the vacuum pump. A small light is turned on and positioned on the top of the cage. The vacuum pump is then switched on and the outer room lights turned off. The cage door is opened and the adults are sucked into the collection tube through the small opening. When Brenna collects, she keeps track of the number of adults caught. When Brenna's done collecting, she takes note of the colony name and records the number of adults collected for that day. Oviposition containers that we use for foliage-reared insects look like this. A large plastic petri dish is glued to the bottom of a clear plexiglass cylinder that is 13 centimeter diameter by 16 centimeter tall. The lid has two screened openings and a center opening that is covered with a flat piece of rubber that has a cross cut into it. Through this cross, we can add adults to the cage. Wide masking tape is then placed over the rubber door and a slit cut into it so that the oviposition sheet can be inserted into the cage. The oviposition sheets measure 3 centimeter wide by 11 centimeter long and are the same oviposition sheets that we prepared earlier in the video. Finally, another piece of tape is placed over the oviposition sheet to keep it from falling into the cage. Cages are then labeled with the date the cage was started, the colony name, the egg generation collected, and the cage letter. We also keep a tally of the number of adults added to the cage each day and record that on a post-it note outside the door. These cages cannot hold more than 200 adults, so once we have about that many, we start a new cage. Just as we did with the diet-reared insects, we change the egg sheets of the foliage-reared insects every day and continue changing the egg sheets for about 7 days or until no more eggs are laid. The egg sheets that were put into the cages yesterday are removed from each cage. The new egg sheets are then labeled with the cage letter and put into their respective cages. The cage letter helps us identify which egg sheet came from which cage so that we can be sure to include the entire gene pool every time we infest the eggs. Since these eggs came from the same colony, they can be wrapped together and put into one plastic cup. Eggs that we don't use right away can be stored up to 2 weeks at 6 degrees Celsius, 16:8 light-dark photoperiod, and 75% relative humidity without loss of viability. Next, we're in the potting shed where we'll show you how we set the plants up. Because it takes 4 to 5 weeks for the plants to grow, you must plan your infest well ahead of time. The plant we like best is oilseed rape or BRASSICA NAPUS. It's ideal because it produces a lot of foliage in a small area and grows rapidly. The starter mix we use is called Cornell mix. It's a mixture of peat moss, vermiculite, limestone, and 10-10-5 fertilizer. Brenna has just finished adding enough water to the starter mix so that it is dense and packs well. The mix is then put into rectangular pans that measure 34 centimeter long by 24 centimeter wide by 6 centimeter tall. About 130 to 150 seeds per pan, or a little less than a quarter teaspoon, is scattered over the surface of the soil. You should store the bulk of your seed at 5 degrees Celsius, 20% relative humidity, and no light, otherwise you'll find that the germination rate will drop over time. If you do not use the same size pan as we do, it's important that you work out the correct amount of seed that will give you the best plant density. Too many seeds and the plants will choke. Too few seeds and you won't have enough plant to feed the bugs. Now that we've finished planting, we'll move the pans to the greenhouse. Our greenhouse maintains 21 to 24 degrees Celsius, and during our spring, fall, and winter months, light is supplemented by metal halide lamps. To give you an idea of how the growing plants should look, Brenna has set out examples of plants of different ages. At 1 week after planting, seeds have just germinated and the cotyledon leaves are visible. At 2 weeks after planting, plants are just beginning to show their first true leaves. At 3 weeks, each plant has about 2 true leaves. 3 weeks is also when Brenna begins to feed the plants once every week with 16-32-16 fertilizer. At 4 weeks, we see 3 to 4 leaves for each rape plant. At 5 weeks, plants have more than 4 leaves each and are ready to be infested with eggs. As you can see, foliage is very green and very plentiful. Remember, healthy plants are the first step to producing healthy insects. If you overwater, then leaves will show patches of beige color. If you over-fertilize, leaves will begin to dry out and get crumpled at the outer edges. Lastly, if the leaves develop a purplish cast, then that means that the plants are not getting enough fertilizer, so you must fertilize more. So now, let's take our 5-week-old rape plants and show you how we infest them with diamondback moth eggs. We use the same formaldehyde method for sterilizing the eggs as we showed you in the diet rearing segment. Just like Jenny did, Brenna is making sure that she uses eggs from all the oviposition cages so that the entire gene pool is represented. If we're only trying to maintain the colony, we'll put about 800 eggs per pan and infest 2 rape pans. Because first instar diamondback moth larvae are not very mobile, it's vital that you cut the egg sheets into long, thin strips so that there's no more than 20 eggs clustered at any point along the length of the strip. Once the egg sheets are cut, they're evenly distributed over the rape plant. Once the pans are infested with eggs, they are placed into one of our large cages. These cages measure 61 centimeter high, 46 centimeter wide, 61 centimeter deep, and are bound with cloth on at least 3 sides. In general, any cage will do as long as there's enough air circulation so that condensation doesn't form on the leaves or cage walls. This greenhouse is set to maintain 27 degrees Celsius, but temperatures fluctuate from 24 to 33 depending upon the season. By the time larvae have pupated, such as on this plant, chewing activity should appear uniform across the pan. If you want healthy insects, then make sure that your larvae are not crowded and have ample food throughout their development. We found that this size plant can take about 150 or so larvae through to the pupal stage. So for the 2 pans we infested for colony, we should get a total of 300 adults or 2 oviposition cages. Now we'll show you how we infest for our toxicity bioassays. We infest the plants at much higher rates, putting on about 6,000 eggs per pan of rapeseed. On the day of the bioassay, we need several hundred late second instars. Because we're putting on so many more eggs, it's critical that Brenna spreads the eggs as uniformly as possible around the plant. The egg sheets were cut into thin enough strips so that there were no more than 20 eggs clustered at any one point along the length of the strip. After 4 to 7 days, depending upon the temperature, we will have more than 1,000 larvae on this one plant, from which we can easily get the 500 or so second instar larvae we need for the bioassay. This plant is an example of a good infest. It's evenly infested without crowding the larvae. These larvae would generate very good data, where control mortality would range between 0 and 2%. This other plant, however, is an example of a bad infest. Some leaves are completely skeletonized, and other leaves have actually curled up and died because too many larvae were present. If you use these larvae in a bioassay, you'd probably get control mortality more than 5%, and you'd get flip-flops. That means that lower doses would exhibit higher mortality than higher doses. Well, that concludes our video on rearing diamondback moths.
We hope you find the information useful.
And if you didn't catch everything the first time around,
there's a written handout included with the video.
bye!